In addition to the homeworks, somebody left behind during office hours 561 project proposal. So if you happen to meet that person, you can run it back maybe after class and just quickly claim it. All right, so that's where I am. Okay, so here's where we were, and I believe that. Well, okay, let me just get you where we are. Okay, so here we have the problem. It's called image segmentation, and in fact, this is a huge topic. A huge topic in computer science and computer vision. So this is, in fact, if you look at the literature, it's enormous. And somebody pointed out again in the class some other approaches to solving this problem. So I'm just going to do one thing here. It's just one thing, and then just show you a couple of ideas that come up. So here's, and I think it's a nice introduction to some of the more advanced applications of network flows. Okay, so here's the, let's say, so I had an image there, but let's make it a little bit simpler. Let's put it here. So here's okay, here's a grid of some sort. Okay, so this grid is in fact a graph, and so each of those intersections here are nodes. So there's a bunch of nodes, and in fact each of these nodes represents a pixel. So these are pixels, and an edge between two nodes or two pixels indicates that they're neighbors. Okay, so you have an image in this, and it's an image is some values for these pixels. But let's say that you're trying to separate one part of the image from another. And here I was trying to separate my hand from the rest of the picture. But let's keep it simple. And let's say I have something like this. Okay, so the image kind of covers these pixels. Okay, so the one I want to separate. Of course, I don't know. In fact, I don't know really in advance what I will separate, but let's say that's what is going to be the foreground. So I want to separate whatever's inside this, which is going to be the foreground, from the background. So the pixels inside this blue area are the foreground, and everything else is the background. So I have to find a partition. So this is a partition A, comma B. So A is going to be the foreground, and B is going to be the background. Okay, so I want to split this up, and the way I'm going to do this is by using some numbers. And so these numbers are likelihood values. So I wrote them down here. So they have a likelihood value for a pixel, have a likelihood of it being foreground or background. And so the likelihood of foreground is AI, the likelihood of background is BI. And I guess these could be likelihood, as likelihood values, they could be logs of probability, probably. Usually is what makes sense. And then for each pair, I've got a separation penalty. That is the separation, that's the cost that you assign to splitting up two neighboring pixels into one being a foreground and one being a background. All right, so in this case, if my pixels, and here the foreground pixels are these, okay, so I need to assign a cost to the separation, and here's how I wrote it. And I know that this was probably not the nicest way to write it, so let me just kind of go over this part again. So the cost I'm going to assign to a separation A comma B, partition A comma B, is going to be the sum of the A values for the pixels that fall in the foreground and some of the B values for the pixels that fall in the background, minus the sum of these separation penalties for all edges I comma j that have exactly one endpoint in the A side. Okay, so so in here, of course, this thing here in blue is the A side, So what I'm adding therefore is the A values for these and the B values for the ones in the background. And then I'm subtracting the penalties for edges that look like this, right? So for instance, this edge goes from the A side to the B side, and so does this edge. It also goes from the A side to the B side, and so on and so forth. So you have a bunch of edges like this, and I'm just adding the penalties for these edges. That's what I meant by this term here. Okay, so these are precisely the edges that have one endpoint on one side and the other endpoint on the other side. Okay, so that's the problem. I want to maximize this value. Questions about this?
So is the penalty the same everywhere?
No, it varies. Okay. The penalty could vary. It could be the same. It's a number. It's been given to you. Okay. Other questions? So the point is, I've got I've got this image. I've got this graph, and I have these numbers. Okay, now I just want to do the split. Other questions? Yes.
What's the usage of the?
Well, you don't want to. Otherwise, if you don't have the penalty for separating, I guess you would you would just put everything in one block, right? You put it all in the A or the B side. So you need to pay something for putting things in different places. Otherwise, you're not going to get any separation of foreground from background. So you do need the penalty. Yes.
So the penalty is given or calculated by the like.
No, the penalties are given, but they have to be calculated somehow, some other way. Okay, so yeah, so I'm given A, B, and the PIJs. Otherwise, I mean, there's other. Of course, there's other. In reality, there's many other things involved here, but let's just assume I've got these numbers. All right. Any questions? So I want to maximize that value. Okay, so let me first of all let's just point out a couple of things. So first of all, I have a cut problem in the sense that I'm separating A from B. That sort of makes it look like a cut problem, and I am penalizing edges that go across the cut. Right. So this is how I'm taking these numbers are kind of like penalties. So it is like a cut problem where I'm kind of penalizing those edges. The difference is that unlike a regular cut problem, I'm maximizing, so I'm not minimizing. And the other thing is that here the nodes themselves have weights. So I don't just have edges with weights, I have nodes that have weights. So I have to take that into account. So so I want to show you, though, in the next several minutes that you can convert this into a standard cut problem. Okay, so this is a transformation which happens to work. And again, if you go into the literature on this problem, you will find many formulations that are kind of like this, much more complicated than this, involve other ratios and things like that, but they all can. Several of them, not all of them, but several of them rely on some idea like a cut, especially the graph theoretic type of approaches. Okay, so let's take this. Let's just go back. Okay, so this is let's see. So I want to maximize. So here's the quantity I want to maximize. It's the sum of AIs. I in A plus sum of BJ's, J and B, minus the sum of the penalties, and this is over all IJ in E such that A intersection I comma J is the size of that is equal to 1. Okay, that again means that exactly one endpoint. Okay, so I want to. So the problem is I'm maximizing this. Okay, so here's what I will do first. So I'm going to claim that. So we'll call this a claim. Maximizing this is equivalent to minimizing something else. So the minimization we're going to try to do is we're going to try to minimize the sum of A, I in B plus the sum of Bj, J in A plus the sum of the Pij's for Ij and E such that A intersection I comma J, size of that is equal to 1. Okay, so this is, first originally we had a maximization problem, now we have a minimization problem. And I'm going to prove it, although I'm going to prove it by writing all the equations. You can sort of see why this works, I think. Can you? I feel like I'm flipping things around. Right? I'm now kind of trying to minimize the things in A that I put in the wrong place, and the things in B that I put in the wrong place. So it's kind of like I'm just trying to, rather than maximizing this, I'm trying to minimize whatever's outside, and sort of kind of reversing it. And now, because of that, the penalties now become positive rather than negative. I mean, that's sort of the intuition, but we need to prove it. All right. So that's the first step. Yes, go ahead.
Does that work as AI for any?
Over all subverted. Okay, now notice that this quantity is fixed, right? So this does not depend on the choice of capital A or the choice of capital B. So for that reason, I can treat this as a constant. Okay, so I'm adding a constant value to this, right? So constant, and so and then what I do is so I'm going to add it, and then I'm going to subtract away the negative of this, which is minus sum of AI, I in A, minus sum of Bj, J in B, of Pij, and okay, so I'm just going to write that this is the same as this. Okay, so this block here is all I comma J and E such that exactly one endpoint is in A. Okay, so same subscript. Okay, so this is the negative. This is just the negative of this. Well, it's negative. It's minus this, minus this. It's minus this. Okay, so I just took this thing and put a minus sign and then just added this constant. And now I think this is what you were saying a moment ago. So what happens is that now if I subtract away from here, right? So if I subtract the i's in A from all of the i's, from all of the a's, what do I get? Okay, so whatever's not in A is going to be in B. Right? So I just subtract away those, so I get whatever's in B. And then similarly, if I subtract away from all of the B's, the part that's in all the little b's, all of the part that's in capital B, then I get whatever is in capital A. Right? So again, whatever's not in B is going to be in A. So I just get exactly the sum, right? So I get exactly the sum I and B plus sum J. J and A plus the sum of these Pij's and the same summation as before. Okay, so it's exactly the same. So I just add a constant, and I think, is that what you were trying to say? Sort of? That this is the way it works? Yeah, sort of, okay. So close enough, right? So we get it. So now I have a minimization problem, so that kind of checks off one box. I want to minimize a quantity which is kind of like a cut. Okay, so now I want to actually formulate a min-cut problem which has that kind of objective function. And here's what I'm going to do. Okay, so I'm going to find I'm going to find a min-cut problem. Okay, so here's my min-cut problem. So right here, and you can do this any which way you want. So here's my original graph, right? So it's got the vertices are the corners of those squares. Okay, so I've got, I suppose, 16 vertices. You can draw them all if you want. Okay, so I start with this, and I need to define a cut, so that kind of flow network. So I'm going to add a source and a sink like that. Okay, and this is going to get too messy to put all in one picture, so I'm just going to show you the relevant parts. So what I will do is I will replace each of these edges by 2. Okay, so I will indicate that like this. So in fact, what happens is that if I have I, J like this, then I'm going to have 2 anti-parallel edges that look like that. Okay, so I'm just going to indicate that like so. Okay, so I have a bunch of anti-parallels. You can see how this gets kind of messy after a while. Right, but I have 2 edges, and I have a separation penalty here for this pair, so I'm just going to make that the capacity of each of these anti-parallel edges. Okay, so I have 2 like that. So you can imagine that, for instance, if this is I and this is J, then this would have 2 edges. Okay, so maybe we can do it like this. So here's I, and here's vertex J, and so this edge here has capacity Pij. In fact, the 2 edges in there have capacity Pij. All right. Now, each of these I and J has a number, has 2 numbers, an A value and a B value. So I will use that in here. So how can I draw this that doesn't look horrific? Okay, so I'm going to put edges from the source to all the nodes. So let's put an edge, let's say, from here to here. Okay, and I'm also going to put an edge from each of these nodes to the sink. And let me, actually, to make this less messy, let's do it like this. So I and J both have edges to the sink, but I'm just going to draw 1 each. Okay, so you have A values and B values. So the A values are going to be used as the capacities for the edges out of the source, and the B values are going to be used as the capacities for the edges into the sink. Okay, so we're going to do this everywhere, so you can imagine that there's also going to be a BJ, AJ. It just gets really very messy, but it's easier to see it in 3 dimensions, right? So you have the source, you have the image, and then you have the source and the sink, and there's just flow going from the source to the image, and then from the image down to the sink. So there. Okay, so this is our min-cut problem. So the vertex set of this graph is just the original vertex set plus these 2 nodes. The edge set is going to be, well, obtained by replacing these edges and further by these original edges by anti-parallel edges and further adding these edges out of the source and into the sink. So that's the transformation. And you can see that, of course, this is a fast, polynomial time transformation because you're only adding adding a linear number of vertices or edges out of the source, a linear number of edges out of into the sink, and doubling the number of edges inside the original grid. Okay, so that's my flow network. And now I have transformed the problem, and now I just have to show that this is going to be equivalent to solving my original problem, which is to minimize this. Okay, so what I have to show is that the capacity of the min-cut is going to be precisely this thing. Okay, so for any cut, in fact, for any cut that I take, any ST cut that I take, the capacity is going to be given by this equation. Okay, so that means that minimizing the capacity of this cut is going to be equivalent to minimizing this quantity, which is equivalent to maximizing what we originally wanted to maximize. Okay, so there's several levels. Okay, so let's just see sort of why, and then you can find the details either in the book or in those slides that are posted. So let's say I have an ST cut. Okay, so here is S and here is T. Okay, and somewhere in there, there's a pair JI, like what I've shown you here, right? So the pair JI, and of course there are two edges in my transformed network. So I have two edges that have cost Pij or Pji, and I've got an A value. Let's call this AI, and let's call it Pj. So the reason I'm drawing it like this is because I want to show you what a cut might look like, and then you can see how this reasoning works out. So the only case I'm really concerned about is the case where this cut separates I and J. So maybe it looks kind of like this. So here's the A side and here's the B side. Okay, so let's see. So do I have this right or not? J. Let's say Pij. AI. Oh yeah. So okay. So there's the B side. So what happens then is that first of all, what's the contribution of this pair to the value of the capacity of the cut? Well, first of all, one contribution comes from this edge, which is an edge from the source to a node that is in the B side. Okay, so I've got so it's some node. It's an A for a node that falls in the B side. So this term, this part here, corresponds to this term. And this other part here corresponds to the B value for a node that's on the A side, right? So again, that accounts for this second term. And finally, well, the last part is what about this? Well, you have one edge going this way and one edge going that way. But of course, the capacity of the cut is only defined in terms of the edges that go from A to B. So you're only counting this edge once. Okay, so you're counting this Pij, you're counting this AI for this node that happens to be in B, and this Bj for this node that happens to be in the A side. And that shows the equivalence between the cut and the original objective function. Okay, so when you minimize the value of a cut, you've actually minimized what you wanted, which maximizes what you originally wanted. Okay, questions? And so there's a, I want to offer some encouragement. When you first encounter this kind of problem, it always often seems to be a sort of tortuous reasoning that leads to the solution. But in fact, once you think about it and draw pictures and just do it over and over again, you can start getting more of a feel for it. Okay, so if initially it seems kind of weird, it gets easier. Okay, questions?
For the same two vertex, the two direction H cannot be occupied in the same time.
Sorry?
So I mean
An edge?
for the vertex J and vertex I.
Yeah.
So the H, P, J, and P
PIJ, yeah, IJ and JI.
So they can't be occupied in single.
They are not counted in the min cut, they are not both counted in a cut, right? Because the cut contains, at most one of these vertices on one side, and at most one of the other vertices on the other. So you're only gonna count this edge once, if at all. Maybe you're not gonna count it if it happens that this falls entirely inside the A side, or entirely inside the B side. But if it's across, then it's only gonna count either this one or this one, because you only count things that go from A to B. Not both, not both. That's the trick in this formulation. Other questions? Okay, so here's another example. This is I like this one even more. So if you didn't like the previous one, so here's an example. Okay, so here's something called project selected. So this morning, I was thinking how am I going to talk about this, and then I thought, I wonder what Wikipedia says about it. So I looked up Wikipedia. Okay, and here's and this example is from Wikipedia. Okay, so here's okay, so this doesn't have to be exactly like I'm showing you, Gary, but this is a typical situation. So typically you have let's say you have, in one typical case, you have some maybe projects, and I don't know, maybe you need some equipment. Okay, so you need to, you're gonna, so the point is, you're going to make money with the projects, but you're gonna have to pay money to get the equipment. Okay, and then you have these edges that indicate that to do this project, you need this piece of equipment. So let's say there's project 1, 2, 3, and here's equipment A, B, C. And in fact, for this project, you need these two pieces of equipment. And for this one, you need B only. Like maybe this project needs tables and chairs, and this one just needs chairs. And this one here needs just that. Okay, so you have 3 projects and some equipment that goes that's needed for these projects, and you have some revenue. So you have you can make $100 if you do this, and $200 for this, and $150 for this. And however, you're going to spend $200 here, and $100 here, and $50 here. So I'm going to indicate these expenditures as negative value. Okay, so okay, so for example, here's let's say I want to do project 1 and project 3. Okay, so for project 3, obviously I need C, and for project 1, I need A. All right. Now, of course, I know you see it that of course that's not sufficient, because this diagram says that I also need B, right? So I need this guy too. Okay, so that's what is in some places called a closed set, in the sense that if I'm going to do something, I'm going to get whatever resources I need to do it, and those are indicated by these arrows. Right, so that's the thing. And now if I looked at this, so this would be, so my set A is a set of activities that I will do, is going to be in this case 1, let's see, 3, let's see, what else? A, B, C. Okay, and that's going to be okay. So I think I think that would be feasible, right? Because I don't need to do 2, but I guess I could. I don't And let's see, so what's the revenue I get for this? You're better at doing sums than I am. Minus 100? Wow, that's not a good choice, right? Okay, so that's a bad choice of activities. In fact, that's really a bad choice, but here's a good choice. I think this is a good choice. So if you do this one, this one, this one, and this one, so here are the squares, I think you're going to make money, right? So you're going to spend you're going to spend 150, and you're going to make $200. Okay, so if I let this be A prime, so the revenue, so if I have A prime equal to 2, 3, BC, then the revenue of A prime is 200. Okay, so that's the problem. So goal is to choose choose a set of activities. And when I say activities, I mean both the projects themselves and the purchasing of the equipment, because you need the equipment to do this stuff. Choose a set of activities that maximizes revenue. All right, and the important thing to remember here, and I'll just emphasize it, is that if I have something like this, let's say I have an edge like this, UV, this means that you must have B to do U. Okay, you must have it, otherwise it's not going to work. So if I choose something and there's an arrow to something else, that other thing has to be chosen, otherwise this is not feasible. All right. Any questions about the problem formulation? So you're going to try to maximize the amount of money you make in this project selection. If you look at the book, at the Kleinberg and Tardos book, you will notice that in fact this graph does not in general have to be bipartite. So you could have a non-bipartite graph as well. In that case, maybe these are not necessarily equipment, but there are other projects that have to be done to do your original project. So you could have something that's not bipartite. That's okay. But again, you choose a set of activities, and you want to maximize the revenue. And if your activity needs something, you better do that something as well. All right. So let's see. So let's see how we're going to solve this. Okay. So. I also want to hand out homework, so maybe I'll just tell you the solution and then we can prove it later. Okay, so here's the, so that's your, that's the original problem. I'm going to, of course, formulate this as a flow problem. Okay, so I'm going to have S and T, and then I'm going to have 1, 2, 3. A, B, C. Okay, so this is the network that's associated with that thing, and I'm going to just keep the directions of these arrows. So this one goes like that, and like this, and like this. And then I'm going to put arcs like this. So the policy is the following. I will put an edge from the source to every activity that generates a positive revenue. So if that number along the node is plus, is positive, I'm going to make that, I'm going to put a source to that, an edge from the source to that node. And if it's negative, I'm going to put an edge from that node to the sink. Okay, so what I will do then is I will put capacity. So the capacity of a positive revenue generating thing is going to be just that number. So I'm going to put 100 here, and 200 and 150. And what I'll do for these that cost money, I'm just going to take the negative of those values. This is going to be 200, and this is going to be 100, and this is going to be 50. Okay, so it's just I just copied the numbers. The pluses just stayed as pluses. The minuses became pluses by doing the negation. And then I'm going to do one more thing. I'm going to add capacities to the edges, the other edges, the original edges. So these will all have capacity infinity. Okay, so that's the reduction. I start from that and I convert it to that. Okay, obviously it takes polynomial time, blah, 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 so it works as far as time. Now, first of all, suppose I have a cut. Well, in fact, let's go even more basic than that. You always have a cut, right? So you can always split S from D. So what if the cut has an edge like this, going from the A side to the B side? What's the capacity of the cut? Infinite, right? So as long as if you select one of these edges, you're done, right? It's going to be too big. So on the other hand, is there a finite capacity cut here? Yeah, of course. I mean, I could choose this guy or this. I mean, you can do. You know, there's finite capacity cuts here. So what I wanted to argue is that every finite capacity cut corresponds to a selection, a valid selection of projects or activities, which includes everything that you need to do whatever you need to do, right? So why would that be? Let's just maybe do one example. Okay, so for instance, correct me if I'm wrong. So let's say I take this guy. So here's a cut. Okay, so here's the A side, here's the B side. Does this cut have finite capacities? No, yes. No, yes, yes, no. Okay, so the answer is yes, because there is an edge of capacity infinity, but it's going from the B side to the A side, right? So that doesn't count. Right, so the only edges that count are the edges that go from the A side to the B side, not the ones from the B to the A. So even though this has an edge of infinite capacity crossing, it's going in the opposite way, so it doesn't matter. Okay, so that I know. Furthermore, let's look at the nodes on the A side. Okay, now I know, okay, and I will claim this, and you can think about it, but I know for sure that this is going to be a feasible set, right? Because if I have something in it, then if it needed something else to do it, it's better to still be on the A side, because otherwise this edge would be crossing the cut, and that would have an infinite capacity. So if something is inside the A side and there's something that it needs, that activity needs to perform it, then this must also be on the A side. Otherwise, this is not going to be a finite capacity cut. So the first thing to notice is that if I look at A minus the A side minus S, this is going to be feasible. Okay, because of these infinite capacity edges, they enforce this requirement that if you have something in, then whatever is needed must also be included. Okay, so that's for sure our feasibility. But what I need to do is establish a relationship between these two problems. And this is what I claim. And I guess I will have to stop soon because I want to hand out homework. So I will show that if I take a finite capacity cut AB, any finite capacity cut A comma B, its capacity is going to be equal to this. the sum. So this number here is the revenue for this activity B. Okay, so for instance, P of 1 would be 100. P of A would be negative 200. Okay, so these are the revenues. This is for all B such that P of B is bigger than 0. Okay, so I claim that this is equal to this minus the sum of PV over all B in A. Okay, and in fact, I should have said that I'm going to assume that that P of S and P of T are 0, so I don't count them in this sum. So if I take any cut, I claim this to be true. Okay, now this quantity here is just a revenue. Okay, because I'm just adding the individual revenues, individual revenues for the activities in the set A. That's just a total revenue. So this is just a negative of that. And what about this value? Well, this value here does not depend on A, does not depend on B. It just depends on the original instance before you try to solve it. So this is in fact like a constant. In a sense, it does not depend on A or B. So, minimizing capacity is equivalent to maximizing revenue. Right. I need to prove this, and I will do that, but I won't do that today because as I said, want to hand back the whole. So this is the connection. And I encourage you before next time to just check this out on this example and see that indeed it happens to work. Okay, so for instance, what is the value of this constant for this problem? What is the value of this first number sum? What is this? Here. I heard it, I thought. 150? This first sum here. Yeah, that first sum, just the first sum. It's what? 450, right? It's just the sum of all the positive ones. It's just the sum of these guys. It's 450. Okay, so just check that that actually works, that this relationship works for this example. And we will get back to that next time. But today I still have another, it looks like 60 things to hand out. All right, so continuing. Jibanata. Susan Maslow. Pejan. Richard Oyeleki.